two, three.
Displacement can seem very easy and a primitive concept, but it's not. It's actually important to understand it deeply. Displacement should not be confused with distance traveled, and this hopefully will help you remember the difference between them. So anytime you look at the etymology of a word, you remember it so much better. So displacement, to displace something, it means to remove it from its original position. And that's exactly what displacement is in physics. Displacement in physics takes into account two positions, initial and final. So here, displacement does not equal to distance. It does not equal to distance traveled, and it does not equal to position. Okay, displacement is just displacement. Okay, let's go through this example together. Let's say that your journey begins in this park and it begins at this point where it says start here and it ends at the finish line, and you're going to walk your dog. So the worst case scenario for your dog would be if you decided to walk it in a straight line, because that's the shortest distance between two places, and your dog would hate it because they love to walk for a long time. But in this case, your displacement, which, as I said, it only cares about two variables, the initial position and the final position. Initial position will be given to you in the problem, or you'll have to define that on your own. So, and the same goes for the final position. So if you did this type of a path, let's say that your the distance between start and the finish is 100 meters, your displacement would equal 100 meters and your distance traveled will be the same in this case. However, if you were feeling like you had a lot of time and you wanted to pamper your dog and you took this path instead, then your distance traveled would be, or how many steps you took, right? It would be way larger than 100 meters, as you can see. This would be, let's say, 5 kilometers or 8 miles. Interestingly, your displacement would still be 100 meters. And that is because displacement only cares about, or it only takes into account, your initial and final position. And obviously, its formula also only includes those two variables, initial and final positions. In other words, displacement is path independent. You could, I don't know, go and land on a moon in the middle of this path. As long as you finish at the finish line and you start at the start point, your displacement for, in this example, will be 100 meters. Now let's go through another example, a little bit larger scale, but it will be illustrative in the same way. We'll highlight differences between distance traveled and displacement, which we're doing to kind of understand displacement, because as I said, displacement is illuminated when you understand its neighbor concept, which are distance traveled, distance, position, and so on. So let's say that my journey starts in New York, and that's my initial position, and it ends in Zurich. That's my final position. Displacement, as you already know now, only cares about those two variables. Now I could take a plane between these two cities, which means that I could take the shortest path, which is straight line, and get there as fast as I can, in which case my displacement would be as small as possible, which is the distance between these two cities, which is immovable because these cities are kind of anchored in the ground and they're not moving. So distance between cities is never going to change. In this case, it's 3,927 miles. But my distance traveled, if I took this green path, would be way larger than that, right? If I made all these stops along the way and then landed in Zurich, it would be way larger than 3,927, which is the smallest possible distance that I could cover to get to the final destination. So displacement, I have a chance to have it as small as 3,927 if I took the straight path there. Now, position is a little bit more interesting. So for you to be able to talk about position, you need to first identify or assign origin somewhere. So in this case, it makes sense that New York is my origin, since that is what I'm counting as my initial position. So let's say New York is where I place origin, or 0. Then I have to count Zurich's position from there. So Zurich and New York are not on the same latitude, but let's pretend they are, so I don't have to bring in 2 dimensions and y-axis. So I can just talk about just horizontal axis, right? So Zurich is 3,927 miles removed or to the right of New York. So that's its position. So if my 0 on x-axis is where New York City is, then x equals 3,927 would be the position of Zurich. And finally, let's go through the last example, which in my opinion is the most illustrative. So let's kind of keep our theme going of airplanes, and let's just jump into the airplane, and let's make the airplane our reference point. So we don't care about where this flight attendant is in relation to Earth, because we just care about the airplane. So let's just, obviously the flight attendant is not jumping up and down, so we do not need y-axis, we just need x-axis. And let's say that the flight attendant needs to get to the third passenger, which is this guy over here. She will travel in a straight line, like so. And let's say that its initial position was x initial equals to 6, and its final position was x final equal to -3. And this is what you need to do. You need x-axis to put the positions there for you to be able to calculate a difference between 2 positions, which is going to be your displacement. So never try to count these dashed lines and then get displacement in that way, because sometimes things can get complicated later in your life, and it's good to stick to a streamlined process to calculate displacement, which is in this way, as I have on the slide, x final minus x initial. You keep negative sign inside of the x final and inside of the x initial if they contain that. So in this case, x final equals to -3, you keep that -3 there, negative sign there. So you put -3 minus just +6, which is -6, and that equals to -9. Now displacement is a vectorial quantity. It's going to have direction, because you would care which way you traveled. If you're traveling 3,000 miles somewhere, you need to know the exact direction, right? Otherwise, you're going to get to a wrong place. So displacement takes into account direction as well as magnitude, which is how far you're traveling. So here, negative represents, as it is the case with all negative signs in front of vectorial quantities, it represents direction, which only means that I have chosen the positive x direction to be eastward, and this flight attendant is moving westward. But I could have chosen my positive x direction to be westward. In that case, flight attendant's displacement would equal to +9. So as you can see, it's again arbitrary, and it does depend on my choice of directions of axes. Here, if I decide to move my 0, which would make sense if the only thing I care about is this flight attendant's movement, then it makes sense that I place origin where she's at in the beginning. Instead of putting x initial equal to 6, I can say x initial equal to 0. That will make things easier for me. So I can do this. In that case, x final will be, if she's still getting to the third passenger, it will equal to -9. And my displacement, obviously formula doesn't change, it's x final minus x initial, and it will be -9 minus 0. I like to keep that 0 there because I like to follow the same exact steps in my solution, because if things get complicated, which they will in physics, you have the same process that works for very easy things as well as advanced problems. So this is a good way to solve it. Always draw x-axis and positions, because positions are your ingredients of getting to displacement. Thank you so much for watching. I hope this video helped you.